Hello! In this video we will talk about the potential energy of gravity so that we can have the tools necessary to solve some orbital motion problems. In a previous video we worked out that the potential energy near the surface of the Earth is mgh, where h is the height above some reference point, which could be the ground. That was fine near the surface of the Earth, where gravity force is simply m times g. However, when we are talking about orbital motion, we are dealing with situations that are far enough away from the surface of the Earth that we have to use this equation for the force of gravity. Because this force of gravity differs from the more simplistic m times g, the potential is also different. Working out the potential from the force requires calculus, so I'm just going to give you the formula as it is usually written. As usual, U represents the potential energy, and G is the gravitational constant. For these problems I will use the big M to represent the mass of the bigger object, which could be the planet, and a little m to represent the mass of the object that orbits the planet, like a satellite. R is the distance between the center of the Earth and the orbiting object. The potential is written such that the values are always negative, except when it is zero. The potential can also be zero when the object is an infinite distance away, which just means when it is so far away that we can treat the force of gravity as completely insignificant. Now, imagine that the object is orbiting at some distance from the center of the Earth, which I will call A. Let's ask the following question. What is the total energy of that object as it orbits? In this scenario, the energy is stored in two parts: the kinetic energy due to its tangential velocity, and its potential energy due to its radial distance a. So our first term is simply half mv squared, and our second term is minus gmm over a. That is our total energy. Now we can actually make this equation a lot nicer, because we know what the orbiting velocity has to be in terms of the gravitational force. If you recall from last video, the gravitational force, gmm over a squared, must exactly equal the centrifugal force, which is mv squared over a. So let's solve for mv squared, so that we can plug it back into our energy equation. All we do is multiply both sides by a. Now let's take this term of gmm over a and stick it into our energy equation. We are left with this expression. That's cool, both terms share a gmm over a term, so we can add them together, and we are left with minus 1/2 gmm over a. That is the energy of an orbiting object. This is a useful result because now we can easily calculate how much energy is required to go from one orbiting distance to another. As a quick example, if you start at a distance of a and want to get to a larger distance of b, how much energy will you need to expend? Well, that's just a question of the difference between the energies at those 2 points. So we would write this equation. You can simplify the equation as this. Whatever that difference in energy is, that is how much energy the ship's rockets would need to expend in order to make that change in orbiting distance. Now, let's do a slightly more involved example. Imagine you have a rock sitting on Earth, and you want to know how fast you need to fling it to have it completely leave the influence of Earth's gravity. That means it won't orbit, but will instead drift out infinitely far away. Let's start by considering the final energy. Assuming it barely escapes Earth's pull with almost no speed left, we can consider the outward kinetic energy to be zero. Its orbiting energy, though, is given by this formula. But since the distance is infinite, the value we are left with is zero. So the final energy is zero. Now the initial energy. At first, your rock has just launched. It has an initial velocity, but it hasn't gotten any higher up yet than the Earth's surface. It is not orbiting, so we don't use the orbiting energy formula. Instead, we have the kinetic energy of the rock, which is entirely due to its initial velocity, and we have the gravitational potential, which is given by minus gmm over the radius of Earth. Now, since the initial energy equals the final energy, we can write this equation. Now, since we wanted to know the initial velocity, we just need to solve for v. First, we move the potential term over to the other side. Then we divide both sides by little m, which gets rid of the little m's. Next, we multiply both sides by 2. Finally, we take the square root of both sides, and we are left with this expression. This is the minimum velocity at which the object would need to be launched to completely break free of a planet's gravitational pull. Just for fun, let's see what this value is for Earth. Here are some values for Earth. If you plug that in, you'll get a speed of about 11,000 meters per second. That is insanely fast. For comparison, the speed of sound is only about 340 meters per second. Basically, that is so fast that we cannot get things to launch out of Earth's gravity by just flinging them really hard. Instead, we have rockets that continuously accelerate an object as it rises, So the energy required to leave orbit is supplied over the time of launch, and not all at once. In summary, we learned that the potential energy of gravity is given by this formula. The maximum value of this potential is 0, which represents an object that has escaped the gravity of that planet. We also worked out the math and found that an object orbiting in a circle has a set energy that depends on its current distance from the center of the planet. We said that to determine how much energy it takes to go from one orbiting distance to another, we can use this formula, which is just the difference in orbiting energies at those 2 points. Finally, we discovered that the escape velocity is given by this equation. That's it for this video. Thanks for watching.